Hello, welcome to Forest Learn. In this case study, we'll be looking at a fun example of projectile motion, namely golf on the moon. This might sound a bit crazy, but it's not. On February 6, 1971, astronaut Alan Shepard, a member of Apollo 14, became the first, and so far only, person to hit a golf ball on the moon. Luckily for us, it was captured on video. So let's take a look at it.
Houston, while you're looking that up, you might recognize what I have in my hand as the handle for the contingency sample return. It just so happens to have a genuine 6-iron on the bottom of it. In my left hand, I have a little white pellet that's familiar to millions of Americans. Drop it down. Unfortunately, the suit is so stiff I can't do this with 2 hands, but I'm going to try a little sand trap shot here. They got more dirt than ball this time. Got more dirt than ball. Here we go again. That looked like a slice to me, Al. There we go. Ready to die. One more. Miles and miles and miles.
After hitting his second golf ball, Shepard claimed that the ball seemed to be traveling for miles and miles and miles. But could this really have been the case? Or was this just an over-exaggeration on Shepard's part? You can find out for yourself in this case study by considering the following questions. The first question is, in order to model the flight of a golf ball hit on the moon, one can use the equations of constant acceleration, the SUVAT equations. Suggest why this is justified. Please pause the video and have a think of this yourself. And when you're done, unpause it and we'll discuss the solution. Okay, so the answer to this is simply that the moon has virtually no atmosphere and can thus be considered a vacuum-like environment. The only force acting on the ball throughout its flight is therefore the ball's weight, and its acceleration is constant, the acceleration due to gravity on the moon. Let's move on to the next question. Shepard used a modified 6-iron golf club to hit his golf balls. Assuming that his second ball was launched at a speed of 100 km per hour and at an angle of 30 degrees to the horizontal, find the range of the ball, which is the horizontal displacement of the ball on reaching the surface again. Express your answer in both miles and yards. And you're also given some conversion info down here, and G subscript moon stands for the acceleration due to gravity on the moon. Let me just point out that we don't know the speed at which Shepard launched his golf ball. So this value of 100 km per hour is roughly half the speed at which a professional golf player would hit a golf ball with a 6-iron golf club. So that seems pretty reasonable given that Shepard hit his ball using one hand and was wearing a spacesuit, of course, which is hardly ideal golfing attire. And again, we don't know the angle at which the golf ball was launched, but 30 degrees seems pretty reasonable. Remember, we're just trying to estimate here how far Shepard's golf ball might have traveled, and with these values we can get a rough idea. So please pause the video here and have a go at this question yourself, and when you're done, unpause it and we'll again discuss the solution. So it's a great idea with projectile motion questions to just start off by getting down a little sketch of what's going on, just to aid you. And as usual, we have to choose a positive direction, right? And we've chosen the upwards direction to be positive. And also remember, in projectile motion questions you have to decide on a start and end. So we've chosen the start quite naturally here to be the moment that the golf ball leaves the golf club, right? So we're told the speed at which it's leaves the golf club 100 kilometers per hour at an angle of 30 degrees to the horizontal, and we're taking the end to be just before the golf ball reaches the surface of the moon again. So recall that we can't take the end to be when the golf ball hits the surface, because at that point the golf ball will experience a force from the ground, the contact force, meaning that its acceleration will no longer be constant and equal to the acceleration due to gravity. And that being the case, that means that the Suvat equations will no longer be valid. So if this point is unclear, I recommend you check out our video that we've created on common mistakes or misconceptions when it comes to projectile motion questions, where you'll find a more in-depth discussion of the things that I've just been talking about. The final thing to note in this diagram is that what we're interested in, the range, the horizontal displacement that the ball undergoes between start and end, I'm just calling that S subscript x. So let's draw up a list of what we know about the motion of the ball in both the horizontal and the vertical directions. Let's start with the horizontal direction. So we're trying to figure out the range. So that's of course unknown. Recall that in the horizontal direction there's no acceleration going on, right? So because the only force acting on the golf ball throughout is its weight, which is acting downwards, there are no forces acting horizontally, because as we discussed in the very first question, there's basically no atmosphere on the moon, so there's no resistive forces whatsoever. So we can call we can say that the initial horizontal component of the velocity, ux, well, that's just equal to the final horizontal component of the velocity. So the horizontal component of the golf ball's velocity doesn't change, in other words. And of course that's because the horizontal acceleration or component of the acceleration is 0. We don't know how long it takes for it to go from start to end. Vertically, what do we know? Well, displacement wise, we know that the golf ball, if it starts at sort of ground level and ends up at ground level, or just before it hits the ground, technically speaking, its displacement, its vertical displacement is 0, right? So we can say Sy, the vertical displacement, is equal to 0 meters. And Uy, the initial vertical component of the golf ball's velocity, well, that's something we can work out, right, from the info we're given about the launch speed and launch angle of the golf ball. So we'll just leave it as Uy here. Vy, well, put a question mark next to that. We don't know what it is. Perhaps we won't need to figure out what that is. The acceleration, well, that's just the acceleration due to gravity on the moon, right? So I'll call that Ay. And since we've taken the upwards direction to be positive, and the weight of the ball is acting downwards, right? That means the acceleration of the ball will be acting downwards as well, because force, resultant force, and acceleration are proportional to each other from Newton's second law, F equals ma. So the acceleration should be negative, minus 1.6 meters per second squared. Again, time, well, that's common to horizontal and vertical motions, and we don't know what that is. So horizontally speaking, in terms of equations for what's going on horizontally, it always boils down to just using distance equals speed times time, right? Because there's no acceleration going on in the horizontal direction. So we can say that S subscript x, the range of the ball, is just equal to its horizontal component of the velocity, which is unchanging, so this constant ux, multiplied by the time to go from start to end. Let's call this equation 1. ux, the horizontal component of the initial velocity, we can figure that out from the launch speed and launch angle. The thing that we don't know is time. So once we figure that out, then working out the range will be straightforward, just multiplying these two things. So to figure out the time, we're going to have to look at the info in the vertical direction. So let's look at what we have. We know the displacement, the initial velocity in the vertical direction, we can figure that out. We know the acceleration, and we're trying to figure out the time. So this suggests using the equation s equals ut plus half at squared might be handy. So let's write that. Sy equals uy t plus half ay t squared. Let's replace sy with 0. And notice here we've got a common factor of t in both of these terms here. So let's take that factor of t out. So let's factorize, and then we've got in these brackets here, uy plus half ay t. So here we've got an equation, technically a quadratic equation, where we've got a product of two things, t, multiplied by the stuff inside the brackets, and the product equals 0. And hopefully you should know that for this to be true, one of two things can either be true. So either we can say t is equal to 0, or the other factor here, uy plus half ayt equals 0. Now this first solution here, this is actually not useful because it kind of just expresses what we already know. It's saying that basically at the start the displacement is 0, and that's obvious, right? Because at the start the ball hasn't gone anywhere. So the solution we're interested in is this one here. So let's rearrange for t here. If we rearrange for t, what do we get? We get t is equal to minus 2 uy divided by ay. Let's call this number 2, equation 2. Note that another way to have worked this out would have been to have worked out the time from the start to the maximum height of the golf ball during its flight. And once you've worked that time out, you can simply multiply that by 2 to get the time from the start to the end. So this might be the preferred approach for some students. Also note that so far we've been working completely algebraically here. We haven't been using any of the numerical values that have been given to us. And this is really good practice, and I encourage you to get into this habit. There's a number of advantages to this. First of all, it's actually a time saver, because you only put in numerical values when you have to at the end. And also, if you make a mistake, if you realize something doesn't seem right, it's actually easier to spot what you've done wrong if you work algebraically, rather than just having a sea of numerical values being multiplied and divided, etc. If you're not convinced of this, I think you will be convinced of the benefits of working algebraically once we've looked at question 3 later on. So let's take these equations 1 and 2 and combine them. So we're just going to pop 2, the expression for 2, into 1. So we get that the range is equal to minus 2 ux uy divided by ay. So we know the value of ay. So the only thing that remains is to figure out the values of ux and uy. The horizontal and vertical components of the initial velocity of the golf ball. So we'll have to use this info about the launch velocity here. So let's use the space up here. We're first going to have to convert 100 kilometers per hour into meters per second. Well, that's 100,000 meters in 3,600 seconds. So we can cancel off some zeros. So that simplifies to 250 over 9 meters per second. So now we can resolve the initial velocity into its horizontal component, ux, and vertical component, uy. So ux is simply given by 250 over 9 times cosine 30 meters per second, which I won't write, and the vertical component is 250 over 9 multiplied by sine 30 meters per second. Alright, so now that we know that, we can just pop these values into, or expressions into our calculator, and just multiply ux and uy together, divide by ay, which is minus 1.6 meters per second squared, and if we do that, what we find is that the range is equal to 417.64 meters, which expressed in kilometers is 0.41764 kilometers. And we can first express this in yards. Remember, the question wants the answer in both miles and yards. So 1 kilometer is this many yards. So in yards, this will just be equal to 0.41764 times 1094, which will equal 460 yards. Just two significant figures. Now, to express the answer in miles, we're going to have to use this conversion info here, that 1 mile is equal to 1.609 kilometers. So 1 kilometer is therefore equal to, let's write it here, 1 kilometer is equal to 1 divided by 1.609 of a mile. So we can use this conversion factor and multiply it by the range in kilometers, which is 0.41764, to find that the range is equal to 0.26 miles, to two significant figures. We'll say more about these results after we've looked at question 3. Estimate the range of the ball had it been hit identically on Earth. Take the acceleration due to gravity on Earth to be approximately 6 times bigger than the corresponding value on the Moon. Assume air resistance is negligible and express your answer in both miles and yards. Let me also just give a hint that in order to answer this question, there's no need to do a full-blown calculation like we've done in question 2. Most of the hard work has actually been done already. So before you launch into some long-winded calculations, just have a think to see if you can spot a nice and simple, elegant way to answer this question. So please pause the video and have a go at this yourself, and once you're done, unpause it and we'll discuss the solution. So we have to try and estimate the range of the ball had it been hit identically on the Earth. And we're told to take the acceleration due to gravity on the Earth, call it g subscript e, to be approximately 6 times as big as the acceleration due to gravity on the Moon, g subscript m. From question 2, we've already worked out that the range is given by the following. Now ay, right, the acceleration due to gravity on the Moon, right, we can express that as well, we know that it's equal to minus 1.6 meters per second squared. But we can replace the 1.6 with just gm, right? So if I pop this into here, we get that the range is given by, so the minus on the top and the bottom here will cancel, so this is equal to 2 times ux times uy over gm. Now if the balls hit identically on the Earth, then that means that both the ux and uy will be the same as before, right? Okay, remember these are the initial vertical and horizontal components of the velocity. So neither of those are changing, and that means that, of course, this whole top here is constant. And what that means is that the range is going to be inversely proportional to the gravitational field strength, which means that if the gravitational field strength on Earth is 6 times bigger than what it is on the Moon, the range will be smaller by a factor of 6 on the Earth than on the Moon. We can see this more explicitly just by writing things out. So the range on Earth is given by the same formula, but instead of gm, we'll use ge, the gravitational field strength of the Earth. And since ge is equal to 6 times gm, we can just make this replacement. And if I just bring out the factor of a sixth at the front here, then we end up with this. And we're done. We're done because this is exactly what we've worked out in question 2. Right? That's just the range on the Moon. And so the range on the Earth is just going to be equal to those values that we found in question 2 divided by 6. Okay? So the range on Earth works out to be a sixth of the corresponding values on the Moon, so namely 76 yards and 0.043 miles. So you might recall in question 2 that I mentioned that I was working algebraically throughout. It was only at the very end that I popped in the numbers to work out the range. And hopefully now you see the point of working algebraically. By working algebraically in question 2, we were able to use this relationship between the range and the acceleration due to gravity, this inverse proportionality relation, to easily work out the answer in question 3. Had we not worked algebraically and just plugged in numbers or numerical values straight away, it's kind of unlikely that we would have spotted this relationship between the range and the acceleration due to gravity. And so we probably would have had to have just work out the range on Earth just from scratch, and thus effectively waste a lot of time. So I strongly recommend you get into the habit of working algebraically. It's a key skill in A-level physics. So we can now assess Shepard's claim that his second ball travelled miles and miles and miles. While it's clear from our calculations that Shepard's shot travelled considerably further on the Moon compared to on Earth, by at least a factor of 6, it seems rather unlikely that it travelled even close to a mile, let alone miles and miles and miles. From our calculations, we estimated that the range of the ball was just over a quarter of a mile. Interestingly, this range of 460 yards is not too far off the current world record of 515 yards. But actually, even this is likely to be quite an overestimate. Photos which have recorded where Shepard's ball landed seem to suggest that it travelled perhaps only around 200 yards or so. So, in conclusion, it appears Shepard was just a bit over-exuberant in his commentary, which is pretty understandable given that he was the first person to play golf on the moon. To finish, I'd like to say thanks to NASA for them releasing their footage into the public domain. You can find a link to the original video in the description. If you found this video useful, please like it, share it, subscribe to the Forest Learn channel if you haven't already, and leave a comment if you have a question or any suggestions. So thank you for listening, and I hope to see you soon.